Hi guys. Just wanted to ask you if you can hear me okay. So my voice is a bit weak today. So
I can hear you. Oh, yeah.
no, beautiful. Appreciate it. Thank you. Yeah, let's just give again always 2-3 minutes to see if anyone else joins. And yeah, and then we'll start. Oh, and actually, before we start, can you please, okay, in the chat, if you can see my PDF, like the share screen is clear also. Okay. Okay, thank you. Appreciate it. Okay, I think we're good to start now. So hello guys, welcome to tutorial 5. Today we're going to discuss the Augmented Dickey-Fuller test, the test for unit roots. So to put it in other words, this is the test that we run to see if we can detect unit roots in a time series, meaning that in the presence of a unit root in a time series is what makes it not being oscillating around the same number, right? So it's one of the conditions for stationarity, the mean that doesn't change over time. So we are going to test for that. So before we go any further, please make sure that you download the dataset in Blackboard. It's called usdata.csv. Make sure you do all the preliminary setup and everything. Working directory, your file, pretty much the data set there. Open a fresh R script and follow the chat, the link that I put in the chat for code share, right? So, so yeah. Oh, I see a few you're already copying from there. That's okay. So yeah, make sure you grab that. You put everything in the in code share in a fresh R script, and then we can start. Actually, before we get into matters, just a quick reminder that this next week, actually Tuesday next week, you guys have the deadline for the quiz, for quiz number 2. So make sure you take time this weekend, go through the test, and yeah, just don't let pass those marks there, and keep working towards that nice final grade that you guys would get. So stop there. It's the deadline is actually 4 p.m. So don't miss it thinking that it's midnight or something like that. And yeah, so yeah, get confused. I think it's been the same, or it's going to be the same for all quizzes this semester. So make sure you take care of that by Tuesday. Also, I had to change my consultation schedule. So it's now in the mornings. So for more information, I put excuse me, I put an announcement in Blackboard. Yeah. So yeah, just stop by there and make sure you get the right timings. So yeah, so just like you actually still have more time to prepare for the quiz Tuesday 12. So yeah, that's I think for next Tuesday, week after that. So still heaps of time. So don't worry about it. But yeah, you can keep preparing for that. Okay, so what we're going to discuss today is how to perform the Augmented Dickey-Fuller test, or ADF. The procedure that we're going to do is that we are going to I mean, what R is going to do is estimate 3 different variations of the Dickey-Fuller equation for a variable, whatever variable we're working with. The first, sorry. The first specific, we have 3. Let me actually display all of them. The difference between the specifications is pretty much how the constant term is expressed. In type 3, the constant term is considered to have a constant, constant value and a trend value, meaning that there's a component that actually changes over time. So this constant term in the equation that usually, you guys remember how mu, the unconditional mean, is determined, like we did this calculation in tutorial 2. It depends on A0, but if A0 has now a component that changes over time, hence the sub t here, that means that it's not going to be constant, right? It's going to change over time. So we call that a trend. And the constant term, we name it as a drift. So a type 3 equation considers a drift and a trend. So that constant term has those 2 bits. Type 2 just considers a constant term that it's different than 0, a drift. So that variation, that number that it goes up and down, it's not 0, but it's a different number. And it also considers A0 to be 0. That's the type 1. So for type 1, we don't have either drifts or trend. We don't consider specifications that have a trend and no drift. So yeah, we're being pretty exhaustive. So the way the rest of the equation works is the same in all 3 specifications. We will estimate delta YT. So we're testing YT for unit roots, but the Dickey-Fuller equation takes first difference of delta, the first difference of YT, but it's estimated against YT minus 1. And a large range of deltas a large range of lags of the first difference of YT. So we can have, for example, 1 to 5 lags. So beta 1, delta YT minus 1, beta 2, delta YT minus 2, until beta 5, delta YT minus Y. So this difference in the number of lags that we put here is where we actually will do some model selection in terms of the ADF. Once we make the choosing for that lag length for delta YT, we will, what the software does is that it will estimate the equation and it will measure, or it will, determine the significance of gamma. If gamma is significant, then we confirm that the process is not indistinguishable from a process with a unit root. Therefore, it's not stationary. So to find stationary, sorry, I don't want to say stationary because you know that stationarity has two terms, right? It's mean and it's also variation. But it means that it's not following those inconsistencies, like all those trends and all of that. So the presence of a unit root is particular for variables that like follow like constant, like it's not going in the right or in the expected path that we have studied. Okay, so just to be clear, stationarity has two components. In this case, we're just discussing the mean. So the test would be for gamma. If gamma is rejected to be significant, then this variable yt will be in the nice behavior that we want, right? That it will go oscillating around a constant value, it will not follow any trends. The mean will be constant. Okay, so we will do that for that data set that we have. So let me jump to R now. I am confident that you guys have the codes in an R script. This R script will also be uploaded to Blackboard by the end of the week, so don't worry about it. But before we go, we will need 4 packages to be installed. I am not going to run this because I already have the packages in my package library. So please take a minute, go through your package library, like you can use the search here, and you can look for the packages one by one. I already have Forecast. I already have dplyr. I already have Zoom. Zoo, sorry, not Zoom, Zoo, and ADSA as well. So make sure you double check. If you don't have it, whatever more packages you don't have, then you run the install packages. And we need to activate or to call for these packages. So let me run off that. It's going to take a bit of a minute. Don't worry about these red letters. It's just giving you some heads up, but no errors, nothing like that. So it's just messages that the program has left for us to like keep an eye on, but no errors. I mean, if it says an error, then it must be a problem. And that's the case. I can give you a hint later, but yeah, don't get flustered by red letters in here or feel like those are errors. And we're going to proceed to load the data. The data set is in a CSV folder called US data. So yeah, it will, if you put it in your working directory and if everything is all set there, it will not be a problem. We have a data set of 3 variables that are observed over 209 periods from the 3rd quarter of 1954 to the 3rd quarter of 2006. So heaps of information there, over 50 years of data there. Let me see if the tutorial questions give any information. Yeah, we have some information regarding log of real per capita GDP of, I assume, the US, given the file name. And we also have the federal funds rate of the US. So that we're going to call that interest rates. So we're going to study these 2 variables independently, and we're going to try to identify any possible unit roots in this. So let's start with YT. The procedure is the same for like whatever variable we will ever do. Later we will repeat, like if we have time, we will repeat it for RT. If we don't have time to do that, I will leave the commands there for you they're already there in CodeShare, so you can do it in your practice time and try to follow. But it's the same procedure. So yeah, we will repeat that. So let's start by plotting the time series and let's see if we can find any potential trends. So the first thing that we're going to do is from this variable, from this data, sorry. From this data, we're going to capture the variables that we're going to need. But instead of having to call from the data and constantly having to, calling variables from there, we are going to capture them and you put them as independent objects. This is a programmer choice. You can you should not that you shouldn't, sorry, you don't need to do this, but I think it makes the programming after this a bit easier. So instead of in terms of Y and R, what I'm doing is capturing those columns and putting them under an object, Y and R. And Eric also captured the information on OBS, which is the date variable in the data, and put it as here, as year quarterly. So the format that this data has is that the information of the year comes first and then the information of the quarter comes second. So we are recognizing that format and also adding that as a new object. We will use this object as our time variable, pretty much for the plots. So let's run also line 18 and we will get our dates here. We don't get any information here, but if you were to display it, so just running the variable dates, you can see here that it's a large vector, 209 points, and it contains the information of all the data, and R has actually recognized that it's year and quarter. So 54 quarter 3, 54 quarter 4, and all of that until third quarter of 2006. So we keep that information there. Then we use plot. We are plotting dates in the x-axis, y in the vertical axis. We are doing this as a line. And we can give some labels to the axis. This is optional, but makes our lives or our graphs look nicer. This is a label for the horizontal axis, and this is the title of the plot. So if we run line 22, 23, we can get this, this plot here. Now, we usually start this analysis with a bit of a night test, right? To see if we can detect any trends before proceeding, right? It's good to accompany every analysis that we make with a night test to see how we are standing there. Oops, sorry, I didn't mean to open this. Okay, so in this case, of course, it's kind of clear that this variable does not follow the same value across time. It's actually constantly increasing and increasing and increasing, following a clear trend. So we are almost 100% confident that this variable will not be considered stationary in mean, right? But we will do the test. Now, let's construct an adequate set of the ADF model. So remember, by adequate set, what we mean is like different combinations of these possible equations. So specifications that have or don't have a drift trend, a drift term, specifications that have a trend term, and specifications that don't, and different combinations of these lags, right? So whether we have, usually we work with lags something in between 0 and actually 1 and no, actually 0. Yeah, 0 is possible as long as we have this term, it's fine. So lags from like 0 to 5, 0 to 10, something like that. So we will calculate a lot of models. The command is a bit intricate, so I will try to go through it. But again, these commands are completely replicable, so every time you will need to use it for yourselves, it will work. So you will not be expected to reproduce any of these codes. These are actually quite advanced, but like, you know, we want to, or Eric wants to give you guys like as many possible tools for your work as possible. So yeah. So what we do is that we want to capture the length of y in a variable called tt. So we have y to that it has 209 variables. So we captured that name here. The L in this means that R is recognizing this variable as an integer. We are also generating an empty list for the estimations of the models, right? Later, we're going to estimate the models. So all of those estimations will be stored here in a list. You remember that analogy that I previously discussed, that a list works kind of as a chest of drawers. So we will pretty much have unlimited drawers here, and each of these estimations will contain a lot of information, will go in each of those drawers as these loops progress. We will put all of these models in a matrix where we are going to compare the information criteria. That's why we name it IC. We will contain 30 models, and we are capturing 5 points of information for each model. We're capturing whether the model has a constant or a drift term or not, whether the model has a trend term or not, number of lags in this term here. Again, anything from between 0 and 5 or 0 and 10, and the information of AIC and BIC. So we start with an indicator of 0 in order to fill each of these rows. So actually, let me run up until this point. And IC starts empty. So starting with an indicator of 0 for every run of the loop, it's going to start at 1, then 2, and it's going to fill all those rows by rows. So it's quite clever to start like that. And in terms of the estimations, we're going to do a nested loop. So we will start with an iteration variable that we're going to call const to represent whether the model has a constant model, a constant term or not, a drift term or not. So 0 for models that don't have, and 1 for models that do. So models that don't have drift will be just type 1s, and models that do have drift terms will be type 2 and 3. We will do lags up to 9. Yeah, again, a choice from Eric. You can also go up to 10. That will not be a problem. This will just add an extra value for I, so it will go moving across the rows. That's why all the indicator for filling rows of the IC matrix and spaces or slots in the ADF lists will follow I. And we will estimate an ARIMA model, right? This model here works if you avoid this term and the trend term. This model looks like an AR model. Actually, we don't have any MA components in there, but of course we will need to put this. I mean, it looks like an AR model of delta YT, right? Delta YT expressed by lags of itself, but we need to bring this YT minus 1 term from outside. So that's why we use XREG. Okay. The order of the ARIMA model, it's just an AR model. So that's why we only iterate P. We don't want to get any MA terms because the ADF models do not have any lags of the residuals. We will include mean, but depending on what the iteration of this variable is. If the iteration is when a variable is without a constant, then this whole argument will be treated as if you put it as false, okay? And false means that it will not add a mean to the model. And yeah, and drift in terms of the computation is a different stuff. So what we mean by drift in the equations, ARIMA considers it as mean. Okay, so that we set this to be false. We will fill the matrix IC run by run. So all these five bits of information will be captured from whatever model we estimate, and will be put in that IC. Now, we don't consider models that have a trend if they don't have a drift, right? There is no delta YT equals delta T. No, if there's delta T, there is a drift. So that's why we put an if here. For models that do have a drift, then we will add a trend term, and that is actually programmed in the model as drift, but this is to add this delta T term. Okay, the rest of the programming is the same. If it doesn't, if this is 0, then it will just do this process as we explained before. So adding this if will allow us to avoid any specifications where we will have a trend but not a drift. So if you must, please run the whole loop together. Do not leave anything outside the highlighted zone. Start with the outer loop and go up until the end, like the last curly bracket. Do not leave anything outside, or the code will not run. If you run it without highlighting everything, it will just show you these plus signs because it's waiting for arguments to close the code. So if you encounter that, just press escape and then go back and actually highlight everything and run it again. Sorry. Okay, so we have our matrix of models. We have a lot of models that do not have a constant and do not have a trend, and all the lags for delta YT. We have some models that do have a constant but do not have a trend, and we have models that have both. Okay, so we added 30 models here. We need to filter by the ones that perform the best, so that's why we order by AIC, so that's column 4, and BIC, that's column 5, and we're keeping the first 10 models. So we get these two nice lists that order the models by AIC and BIC. So I do have the lists in here. What we're going to do is, well, try to find models that, specifications that are in both equations, right? So there are not too many that are in both. Oh no, actually the first 5 terms in the first 5 specifications in terms of BIC are in both equations, in both tables. Sorry, 111 is in here, 112, 101, 102 as well, 113, I think it's all, yeah. So we're going to keep these 5. We could also take 103, as I can see here, and 114 also, and that's it. But as long as we get 5 or 6, that's good. So I think Eric wanted to keep the rest of the output quite simple. So we're going to roll with this first 5 specifications. If for any reason we will have to void any of these, then we can always come back and pick the other 2 that we left behind. So we're going to grab those 5 models. So we're going to put those 5 specifications, so capturing the first 5 models in BIC into an adequate set, and then by comparing that adequate set with the matrix IC, we can get the indexes for these models, which row that model is located in this list, right? For example, for model, which one was the first one that we have? Sorry, for model 111. That 111 model is in row 22, right? 111 here. So that's why 22 is in here as the index. So yeah, we are getting those. So later when we go for this list that has all these estimations, we have all the models that we estimated, we can come back and grab model 12, model 13, model 22, 23, and 24. Okay, up next, we are going to check the residuals. So we are going to run the check residuals command that we have used before for the models. And in here, we will use the index as the index that we created, right? So it's going to loop through the components of this adequate index object. So we can run the for loop, and it's going to take a minute to produce all the Lyon box tests. We need all these specifications of the ADF to be white noise residuals. So we need to double check that. So that's what we're doing in this step. So before actually checking the results, I would like just to look at the graphs, and graphically the residuals look okay, right? They don't look like they follow any trends or anything like that. So they look okay. So let me just wipe this view here and go to the slideshow. So the graph looks okay. Then we go and actually check the p-values. Remember that the new hypothesis of the Lyon box test is that the residuals are white noise. So we want models that we fail to reject that null hypothesis. In this case, all the p-values are higher than 0.05. So we will reject, we will fail to reject the presence of white noise residuals. So all those 5 models are good for estimating the ADF equations. So let's do that now. So using the command it's quite simple, adf.test and whatever variable you are evaluating. And R is going to do, let me expand this. It's going to do with the 3 specifications that we discussed, no drift, no trend, drift, no trend, with drift and trend for the first 5 lags. No, actually for the first 4, so 0, 1, 2, 3, and 4. So actually, let me go back to the slideshow. Those P's are what we are changing in here. So it starts with nothing, so only these terms, then we'll add 1 delta, then 2 deltas, 3 and 4 deltas to the model. That's this difference here, and we'll test the significance of gamma, okay? So these p-values are given here. But we need to be careful, because if you notice from our chosen models, let me display actually this matrix. These are the models that we're choosing. We are like the models that we chose have drift, no trends, first 2 lags, then drift and trend for the first 3 lags. Okay, so we only look for those models in this output. So we have drift, no trend for 1 and 2 lags, I think, and drift and trend for others. So I actually have it in my slide. So we only look on that output for those, for those specifications that we have in the model. Okay, so we have specifications with drift and no trend, and with drift and trend from I think it's a bit of a mistake here on my end, to be honest, because adequate said, yeah, lags 1 and 2. Sorry, that's my bad. So let me fix this right away. It's not lags 0 and 1, it's lags 1 and 2, but anyway, the result is the same in 1, 2, and 3. The result is the same either way. We will fail to reject the presence of unit roots in here for the specifications that we chose. So we are confirming, or not confirming, we are finding evidence that this process has unit roots. So please remember the correct wording for this. It's called like this process, YT, is not empirically distinguishable from an integrated process with a drift. So it means that we don't have enough evidence to find a difference between a model that has unit roots, not a model, sorry, as a process that has a unit roots. Okay, therefore this time series is not stationary. I think I skip here a little bit. I just wanted to discuss like more of the Dickey-Fuller test. Like I mentioned, it will estimate the correct specifications, and what I wanted to remind you is the null hypothesis. We're testing for gamma, and if we find that, like if we reject that gamma be equal to 0, then we will find evidence that this process is empirically distinguishable from an integrated process. So that's good, right? We want to reject the null hypothesis in the Dickey-Fuller test. Unfortunately, in this case, we didn't. So the way to proceed is that we will now find the first difference of YT, and then we do the test to see if that works. So that's a golden rule. If you must, if the Dickey-Fuller test, I mean, if the variable in levels does not work, then just find first difference and go for it and test. Most of the time, I would dare to say 90% of the time, it will solve the problem. It's very unlikely that we encounter time series with more than one unit roots. So usually first difference is more than enough. So let's repeat the process for delta YT. So we will do again model selection for the Dickey-Fuller test. So that's what we're going to do up next. But now instead of working with Y, we're going to work with the first difference of Y. Eric chose to not create the variable diff, but to use the operation here. It will work just as well. But the only thing to be careful is that the ARIMA specification is for the first difference of whatever variable we are using. So we will be taking second difference, right? It's the only thing to be careful. Everything else will stay as we discussed before, different specifications of P, different combinations of drift and trends, or drift with no trends or no trends. So I will just go ahead and run the whole bit again. Just give it a second. It's usually not too, this process is quite complicated, so it will take a minute. Okay, so we have these lists of the best models of AIC and BIC for the first difference of Y. So we have this list here, and we found that the first 5 models in both lists are the first 5. So this is actually quite a great result. We often don't find this, but when we do, it's an advantage. We are kind of sure that these are the best models. Actually, if you notice, 112 and 103 are also in both lists. 113 and 104 are also there in 104. Actually, the top 10 are the same. Now that I look at it, yeah. So if these 5 models don't work, then we can go with the next 5. So that's good. These lists, when they are consistent, that's great. So we are going to proceed and like create that adequate set, capture the indexes, and check the residuals. So I'm going to run all of these at once, since we already know what they do, and we will check the Young box test for the white noise residuals. So it's still going. Every time you notice that R has this bar that it's blinking, it's R telling us, just give me a second, let me do my thing and just chill for a minute. So let's just give it a bit of time. Okay, so we can see that for all the models, like the graph looks fine. Then for the other model, it's okay. Graph looks fine. It looks okay here as well. And looks quite okay. Here also as well. So it's good. The eye test was passed, but of course we need to do the formal test. So we will look, the output that we have here in the console. I just summarized it here in the slides. We failed to reject the presence of white noise residuals. Therefore, these models, all 5 of them, are okay. So now what we are going to do is, with those 5 models, perform the Dickey-Fuller test. So we're going to run that. And we get these results. I have the suspicion that I actually didn't highlight the right models again. So it's 0, 1, 2, 0, 1. Let me see. Yeah, I know. So it's 0, 1, and 2 for those 2 models, and 0 and 1 for the other. But, it's just that I got misled by these indexes here instead of actually looking for this. But regardless of that, you can, I moved the slide that shouldn't. But anyway, we notice that we will reject the presence of unit roots anyway for whatever lags. So it's the great result. We confirm that actually after taking first difference of YT, this process now is distinguishable from an integrated process. So YT, at least in mean, delta YT, sorry, at least in mean is a variable that we can consider stationary in mean, okay? And later in the semester, we're going to see how to treat those wild peaks in terms of variance. But for now, we're just focused on the means. Okay, so that's the way that we will test this. The final bit is that we will do a little bit of model selection in terms of what ARMA models we will estimate, right? So we will, this loop is like a lot more complicated because the specifications for the ARIMA model that we will consider, because the whole deal behind this is how to better forecast this variable, this data, right? So what we need to do is to use a lot of specifications and find the best. The specifications might have a constant term, might have a trend, might have a first difference or not, in whatever lags of AR and MA. So AR and MA. Okay, so we do have a lot of stuff changing. We will now range also for first difference or not, and we can also consider drifts and trends. So we will bring that, all of this. This is the calculation that Eric came up with to calculate the number of rows in the information criteria matrix. It's not something that I will be able to explain at the moment, to be honest. But in due time, you can always count like how many variables you have. You're changing this from 1 to 2, you're changing 0 to 1, so that's 2, 2, 4, and 4. So what happens from 4 times 2 times 2? 64. I think that is also something, but it depends on the combination. So for this, I will have to come back to you and know how to, and how to calculate this, but don't worry about it. For now, we will just create that empty matrix and run all of this because we want to look at information criteria. So what I'm going to do is run all the preliminaries of the loop first to create the empty matrices and the empty lists and all of that. And then we will estimate the models. So the way the ARIMA model will be estimated, you guys remember changing P, D, and Q, depending on if you have a constant term or not. You will include that as a new term. So if I'm including a constant, then C1 will be taken as true. So it will include a constant in the specification. And if we do have a constant and we do have a a trend, then we will add that as well in here with the include drift argument. So it's taking all of those possible situations into consideration. But again, this code is completely replicable, so don't worry too much about like the little bits of it. Let's just run it. And yeah, if you're ever like needing to adjust it to your own work, please come to us and we will be more than happy to give you a hand with that. So it's there now. It's actually done. So let's get the best specifications for AIC and BIC. So I do have those in here. We will use something, actually I forgot to mention, we will use something called intersect to find, because we have like now, where is it? Sorry. We have now 5 terms in here. So comparing 5 terms in both lists might be too tedious. So this intersect command allows us to look for rows that are the same in both lists. So using that will give us this list of models that have that are in both lists. But if you notice, all the models that are chosen did not consider a first difference of YT. So it's taking YT as in levels. And we know that that is not good for ARIMA models in the long run. They can still be used in short periods. And it seems that they are the ones that perform the best, like they do provide the best fit. So we should use them, but we accompany them with a few of the models that do have a first difference and appear in both lists as well. So we will add those models here and we will run with the 6 models. We added these 2 because we found that it's better to take first difference of YT for this bit. So we will capture the adequate set in the index. The variables are created, and the next check before actually doing forecasting using ARMA models is just checking residuals. So let me wipe these graphs in here. So we will get fresh graphs, and we'll give it a second for it to work. By the way, if you ever like find that R is taking ages to compute and you wanna like stop it, you can click here on this red stop sign and R will stop trying to calculate what it is calculating. So sometimes we make a mistake and like, you know, program an infinite loop or something like that, and we notice that it's taking way longer than it should. We should like stop it and see what happened, no? But that's just for like a programming standpoint, not an econometric standpoint. Okay, so the models here, this looks okay in terms of residuals. This looks okay. Again, in these graphs, what we're looking for is to like find every like constant ups, constant downs, or a constant a constant evolution, something like that. We want them to go like a heartbeat, right? Like up and down, and no weird stuff there. So that's okay. And then we will check the results here. So I have summarized them in the slides. So we look at the p-values, and all of those 6 models are okay. So we can use them for forecasting, but of course, please be careful. Like, you know, I need to tell you this in case you are ever asked. You can use models forecasting with ARIMA models of non-stationary time series, but only are reliable in the short run. You guys remember that we saw that in a previous tutorial, that in the long run they get haywire, they go crazy. So we don't want that. They can be used, but only for short periods of time. And another thing that I always like to repeat in this particular tutorial is that the test for white noise residuals, please remember this, is called Young-Box test. And the null hypothesis is that there are white noise residuals, and we want to fail to reject. The test for unit roots is called Augmented Dickey-Fuller, ADF. And the null hypothesis is that there are unit roots present in the process. We want to reject that. Okay, so please remember those 2 models. I'm almost 100% sure that it will be asked in an exam or something like that, something that we would expect you guys to know. Okay, so please don't lose any silly marks with that. Okay, so that's the whole process for every model. Even if the codes look a bit complicated, the process per se is not it's not too complicated. I don't want to say easy, but it is. As long as you follow the steps, you will be fine. So we actually do have time to do it with R. So I'm going to repeat myself. The process is going to be exactly the same. So yeah, let's just actually, I think we can take a minute, and I will take questions from you if you have any. So please let me know. Okay, let's keep going. Luckily we have time, so let's do the process now for R. So R is the interest rates, the federal fund interest rate. So let me wipe the graphs here, and we can always wipe the console here. If we don't no longer need the output there. So let's plot it. The syntax for the plot is the same, but now we're plotting for R, and you can see here that even if R doesn't seem to follow an upward trend or a downward trend constantly, like across time, it does have a combination of them, right? It goes like it's not going up and down around the same number. You can see the mean evolving over time and following this path first, and then evolving over time and following this path second. And as it looks here, it seems that it's going the other way around. It's keep going up. So even if it doesn't look like not all non-stationary time series look like this, this is also not a very good look for a variable in terms of stationarity. Okay, I just want that to, I want you guys to remember that. All right, now for question B, we are now going to select models for the Dickey-Fuller test, right? So remember specifications of those 3 models with constant and trend, with constant no trend, and without either. So the code here is exactly the same. I checked. So we are going to generate that list of AIC and BIC with the model. Again, it's going to take a hot minute there. So just need to be patient for a minute. That's the list is done. I like this method to compare and get the models that are in both lists. I love this. So I encourage you guys to use that intersection command, and we can see that these 3 models are the ones that perform the best in terms of both AIC and BIC. We have a drift, no trend at 6 lags and 7 lags, and no drift, no trend at 7 lags. So that's good. Those are the models that we're going to use. So let me check. Yeah, those are, they appear in both lists. So we're going to use that. Now let's go and do residual analysis. Okay, we captured the adequate set and the indexes and all of that because we want to check the residuals. So let's run that and let's check. It's one more. Yeah. So in terms of this looks okay. So they will, I think they will all pass the eye test. That's fine. Yeah. In terms of graph, it looks okay, but of course we want to look at this. And when we look at the Young box test, we are rejecting white noise residuals for the specification at 6 lakhs of drift and no trend. We confirm white noise residuals for these two models. So in this case, we could do two things. We could go back and select another couple of models to replace this one, or we can just void this one and keep going with these two, but it's important to be mindful of this. So I noticed that the solution guide is a little bit lenient in that case. It's saying, okay, let's overlook this, but I actually, I'm talking with Eric about this. It's important, right? It's important to acknowledge this. This model is not presenting any indication of white noise residual, so it should not be reliable for an ADF test. And actually, this is why we don't look at the whole list of the ADF tests, because some of those models are not okay. So they should not be part of the decision process. So what we're going to do is do the ADF test. The command is changed slightly because the default setting of ADF test is showing you 4 lakhs, 0, 1, 2, 3, and 4. But I wanted to be up to 10 because the models that we're choosing have up to 6 and 7 lakhs. So we want to reflect that, right? If we leave it as it is, we will not actually be visualizing the models that we chose. So let's run it and we will get this list. This list is now slightly larger. It goes up to 9 lakhs. Remember that it takes the 0 into consideration. And these are the 3 models that we specify. And you can see here how the 6 lakhs here is giving us contrary results to the other 2 models. So that's why I should put this as a red square there. It should not be considered, right? We are failing to reject for the models that we chose the presence of unit roots. So the results in particular for the specification are a bit different. We failed to reject in some, we will reject in others. My best guess there would be that few of these models, if not all of them, have problems in terms of residuals. Okay, so that's why that step is very important. So sorry about this. Well, technically this one is larger than 0.05, but as a rule of thumb, we would prefer larger numbers in here. But anyway, we are failing to reject that presence of unit roots. So we will need to take first difference of R and go through the whole process again. So that's what we're going to do. But now we are doing it for the first difference of R. So we are replacing everything that was R in this model, right? You notice how it's diff of R, and in here is diff of R. Okay, so we're replacing all of that in the model, putting everything in there. And let me just go on and run the model again. We run the model, we will look for which models are in both lists and get the indexes and the adequate set of models. We'll notice that these two, what happened there? Sorry, my bad. The list is, I didn't put there correctly. Let me find the one in here. Yeah, 006 and 007. So no drift, no trend for 6 and 7 lags are present in both lists. So it's actually here, but this square is misplaced. Sorry. So it's 006 in here and 007. So it's present in both lists. So those are the models that we're going to use for the Dickey-Fuller test. Oh, actually, we need to check the residuals of those two models first. So let's cross our fingers for good residuals. For 600 looks okay. And for 70 is also okay. And the graphs look good. Let me see the 6. Yeah, it looks fine in both cases. So we will proceed with these two models for the Dickey-Fuller test. If you noticed here, both specifications do not have a constant and a trend. So we will only, when we produce this ADF test, we will only look at specifications of type 1, right? No drift, no trend. So that's why I only kept that list in here. We don't have any adequate models that are type 2 or type 3. So when you look at that table, and if you look here, we will reject the presence of unit roots in both models. So that means that they are empirically distinguishable from an integrated process. Okay. So yeah, we confirm that we can use RT to do forecasting. We were asked not to repeat the process of the forecasting for R as well. The process is a bit long and you guys are already familiar with it. But yeah, this is the way that we will test for the presence of unit roots. Please remember the procedure. It's a bit long, but it makes sense, right? So please remember to check it, to remind, and please remember the conditions for the tests. Remember that the tests need to be like what the models, the adequate models need to be white noise residuals. Then what do we check in the Dickey-Fuller test and all of that. Alrighty, guys, that's all we are going to discuss today. Thank you so much for stopping by. And yeah, I will upload the recording later. And the R script will also go there as well in Blackboard. So thank you so much. And I'll see you guys around. Thank you.